momentum. So we had this example that we were looking at. And what we showed here is that we analyzed this thing and we ended up calculating the impulse for this rocket. So let's interpret this question first. And what we saw here is that in space, we had the thrust of the engines go off. And the thrust curve is this force versus time curve over here on the right here. So what we're seeing here is that they wanted us to calculate what the impulse was. And so the way I see it here is that I have a rocket. Okay. What does my rocket look like? Here's my rocket right here. So when I think about my rocket, I imagine that I have these I guess, wings here. And what's happening? Well, if you believe the movies here, the thrust is now going off here. And what we see here is that the rocket now starts off with some initial momentum, P1 going to the right here. And as a consequence, there's the impulse of the thrust. So now what the impulse does is it now applies a thrust that has an external thrust, which is given by this quantity. And as a consequence, it should then increase the momentum of the rocket. So if I was to draw this on a bar diagram, I see that the momentum of the rocket initially starts like this. And what happens? The thrust comes in and it adds this much impulse to the rocket. But the impulse doesn't disappear. What it does here is that it transfers to the rocket. So in this case here, now the momentum of the rocket is larger, and it's, again, moving to the right. So what I've done here, which I didn't say before, is that I made that my positive, this negative direction. So this is our mathematical equation. This bar diagram is telling us exactly how to write the equation for this system. So that being said here, what I want to go and do now is that I want to go and I want to focus on the impulse. So if I look at the impulse, that means I got to look at the force versus time. So let me get that curve. So now, to calculate the impulse, we need the area. And so now if I come in here and I paste this graph here, my whole goal is to calculate this area. I need this area right here. And because this is a triangle, we know exactly how to calculate this area, because that's just the area of a triangle. So now, if I look at the area of triangle, I know it has to be 1/2 times the height times the base. So if I start to put that together, I can see here is that this reads that this is 1/2 this thing here is then going to be my max force. And then from here to here is going to be my contact time, which is 30 seconds. So then the height here will be F max times my contact point. And this is also equal, from the mean value theorem of integrals, this is also equal to the time average times delta t. So if I look at this thing, here's what I find here. That the area in this case is going to be 1/2 times the maximum force, which is 1,000 newtons, times 30 seconds here. So you could see that the units of the impulse or momentum is going to be a Newton second right away. So you'll see here is that I have 30 divided by 2. That's going to give me 15 times 1,000. That should give me 15,000 Newton seconds. And this is the value of the impulse produced by the thrust. So even though the question does not ask for the average force, we can compute the average force. So if I look at this thing, the average force is then given by the relationship of the area, which is 1/2 F max delta t, and this will be F average delta t. But if I just focus on the last two terms, you can see here is that the time cancels out, and it says here is that the time average force is 1/2 F max. So in this case, this will be 1/2 times 1,000 newtons, which is then 500 newtons. Not 5,000, but 500 newtons. So if I look at this curve again, what this average, again, what it really tells us here is it tells us what? Let me see if I can copy this again. It says this. I have my impulse curve. And I know that the area, right? I know that this area here is equal to 15,000 Newton seconds. So what does that average force here? So I'm going to say that this is half of this. So this guy right here tells me that this guy is going to be 500 newtons. So if I now calculate the area all the way to here, it turns out that this area right in here in green, this area where I picked that average here, this also has an area equal to 15,000 newtons per second. Those two areas are equivalent. And because of this, this then tells me that when I calculate the area or the impulse, I could either use the term 1/2 F max times the base, or I could equally use the average delta t. This, as I said before, is very powerful to have in our corner to be able to use that. But that's what it means for the impulse here. Now, let's go look at the question again. let me bring this question back, and I see this here. So now if I look at the second part of the question, we just answered the question about the impulse. Now, at what time does the rocket reach its maximum speed? And this was the question that I asked in lecture, and if I remember correctly, Owen was the one that really answered this by saying here is that at what time does the rocket reach its maximum speed? It's at 30 seconds. So the question is, why does the rocket reach max speed at t equal to 30 seconds? Well, the way to think about this is think about pushing a car. So if I was to have an analogy, it goes something like this. I have a car, and you could imagine that you're going to be pushing this car. Right? So as you're pushing your car, or as you're pushing your friend's car, what are you doing here? You're pushing it, and you could imagine that you're feeling strong here. So as you're feeling strong, so initially, you feel good. And what do? You push harder and harder. So what happens here is that this car now is starting to speed up, right? It's getting faster and faster and faster. But you could imagine here that you get to a point to right here where you can't push any harder since you are tiring out. So what do? You continue to push the car. So here, what you're finding here is that this force is getting big here. So you're applying a big net force right in here. And then a little bit later, what you're finding here is that now you can barely push the car. But you're still pushing the car. The car continues to go faster, but now the force that you're applying here is not as great. You now have a smaller net force that you can apply. So as a consequence, your force is not getting bigger. You've already peaked out. It's now getting smaller. Nonetheless, you continue to push. So you continue to push while tiring out. And so what that implies here is that the car still speeds up, but not at the same rate. So that's why at 30 seconds, this gives you max speed. So then if I come back here to my bar diagram, let's get my bar diagram. We've already applied the impulse momentum theorem. So now, here we go. We're going to apply the impulse momentum theorem to calculate Vmax. So if I do that, that's just my bar diagram. This is it right here. This is my bar diagram now. This is our mathematical equation. And I can see here is that it says this here, that P2 equals to P1 plus J of the thrust, which then just means here that this is going to be mass times velocity 2, mass times velocity 1, plus the thrust that we have already calculated. So then I'm just putting in my values here. So what do I know about the problem? The problem tells me that the mass of the rocket is 425 kilograms. We know that its initial speed was 75 meters per second. And we also know that the impulse that we calculated was 15,000 newtons per second. So I could just put those numbers in. So now, if I look at this thing, I'm going to remove this over here a little bit more. So now what I'm going to do here is that I'm going to solve for max speed. In this case, we define this as V2. So if I divide both sides by mass, I'm going to get that V2 is then going to be V1 plus the impulse of the thrust divided by the mass. So then I'm going to get 75 meters per second plus my thrust here, which is 15,000 Newton second, divided by the mass, which is 425 kilograms. And if I compute this number, let me get that number, I get that this is 75 meters per second plus, what is that? I got 35 meters per second. So you could see here is that this was the increase in speed by the impulse of the thrust. So that gives me a value of 110 meters per second, and that's going to be my maximum speed right there.